Hello, my name is Jared, and today I'm going to talk about multi-component steady-state diffusion of a gaseous mixture in a Stefan tube. And so let's talk about the little scenario we're going to talk about. We have a liquid mixture of acetone and methanol, and this mixture is going to evaporate out into this airstream we have up here. So up here we have air moving across the top of the tube, and it's going to carry away with it the acetone and methanol as it moves across. And we're going to call this liquid vapor interface right here. We're going to use that as a reference frame, and we're going to call that Z equals 0. And then up here, where the air is moving across, we'll call that is equal to Z equals, it's 0.24 meters. And we're going to use the variable to represent that. We're going to say that that's equal to delta. And since up here, it's just air moving across, and the air is taking all the acetone and methanol that diffuses, that evaporates upwards. It's taking all of that away. We can practically say that the amount of acetone and methanol that's up here in this airstream is equal to 0 for all practical purposes. So we can neglect that the concentrations of acetone and methanol up here at C equals delta. So we can say that the mole fraction of acetone is equal to the mole fraction of methanol, and both of those are equal to 0. And again, this is at delta, which is Z equals 0.24 meters, which is 0.24 meters above the liquid vapor interface. And down here we have a mixture of acetone and we have a mixture of methanol. And with this mixture, if we assume an ideal solution, we could use, if we were carrying this out in a laboratory, we'd be able to calculate the vapor pressures of each component right at the liquid vapor interface. And from that, we could calculate the partial pressure of each component, and therefore could calculate the mole fractions of each component. Luckily for us, we already get the mole fractions of acetone. So Y1, we're going to use subscripts 1 equals acetone, 2 equals methanol, and 3 equals air, just to simplify it so I don't have to say the mole fraction of acetone every time, or the mole fraction of methanol. So the mole fraction of acetone right at the liquid vapor interface is equal to 0.319, and the mole fraction of methanol at the liquid vapor interface is equal to 0.528. And so these numbers practically come from Rayoult's law, but since this isn't an ideal solution, you'd also have to take into account the activity coefficient and to be able to calculate the actual mole fractions of each. Luckily for this problem, we're given both the mole fractions, and we could easily calculate the mole fraction of air at the liquid vapor interface due to the fact that the sum of all mole fractions are equal to 1. And so what's given in this problem is the Stefan-Maxwell diffusivities for each pair. So if we have 3 components, air, methanol, and acetone, then since the Stefan-Maxwell diffusivity for acetone and methanol is the same as the Stefan-Maxwell diffusivity for methanol and acetone, then we get 3 different Stefan-Maxwell diffusivities. So the Stefan-Maxwell diffusivity for the acetone and methanol is equal to 8.48 millimeters squared per second, and then the Maxwell-Stefan diffusivity for the acetone and air is 13.72 millimeters squared per second. And then the Stefan-Maxwell diffusivity for the methanol and air is equal to 19.91 millimeters squared per second. And we're also giving the pressure and temperature for this system. So the pressure is equal to 99.4 kilopascals, and the temperature is equal to 328.5 Kelvin. And we assume during this entire process that the pressure and temperature are constant, and therefore the total molar concentration is constant throughout the entire process, because we're assuming ideality for the vapor phase. And so we can apply the ideal gas law, PV equals nRT, so N over V equals P over RT. And since P and T are constant and R is just the gas constant, then we can say N over V is constant, so the total molar concentration is constant. And something else I'd like to point out with this problem is that air here isn't diffusing. I shouldn't say that. There's no molar flux of air going down because the air isn't very soluble in the acetone and methanol mixture. So for simplicity's sake, we can say that air doesn't exactly dissolve in the acetone and methanol mixture. And so we can say that the total molar flux of air must be equal to 0. If it's equal to 0 here and equal to 0 here, it's what we call stagnant. So it's diffusion of methanol, acetone and methanol in stagnant air. The air isn't flowing downwards at all because it can't go into the liquid phase, because we're assuming that it can't dissolve in the liquid phase. And since the molar flux is constant, 0 here and 0 here, we can say it's steady state. And just because the air is stagnant doesn't mean that it's not diffusing. Because what happens during this process is that we have acetone and methanol evaporating, and there's a total net flux, molar flux, upwards. And so for air to stay stagnant, we know that the molar flux of a component is equal to the molar diffusive flux plus the mole fraction of it multiplied by the total molar flux. So actually what is happening here is that air has to diffuse downwards to counteract the total molar flux in order for it to stay stagnant. Kind of like a fish that is swimming through a stream. In order for it to stay in place, it has to move exactly to counteract the current to stay at the same position. And so with all that with consideration, what we're trying to do here is we're trying to calculate the rate of evaporation for acetone and methanol. And at first that seems kind of difficult, but really what this is asking is that, well, what is the molar flux of acetone and what is the molar flux of methanol right at the liquid vapor interface? That is exactly what the question is asking, just wording it differently. And after we calculate that, we want to calculate the concentration profiles. So how do the concentrations, the mole fractions of each component change with the z direction? And so first thing I want to consider is that we're given the Stefan-Maxwell diffusion coefficients, right? And the governing differential equation for diffusion is the Stefan-Maxwell equations. First thing I want to write down is the Stefan-Maxwell equations. So let's do that. So Stefan-Maxwell equation. All right, so we have the derivative of the mole fraction of component 1 with respect to z. That's the mole fraction, derivative of the mole fraction of acetone with respect to z. That's equal to, I cannot write, that's equal to mole fraction of acetone, and 2 minus Y2 and 1 for C, Maxwell diffusivity of 1 and 2, minus Y1 and 3, minus, well, this is a plus actually, minus Y3 and 1 over C D 1, 3. I'm not saying what these variables are out loud because the way I memorize it, I'd not be able to. So if I go back, it's the derivative of the mole fraction of acetone with respect to the z direction is equal to the mole fraction of acetone multiplied by the molar flux of methanol minus the mole fraction of methanol times the molar flux of acetone over the total molar concentration times the Stefan Maxwell diffusivity for acetone and methanol plus the mole fraction of acetone multiplied by the molar flux of air minus the mole fraction of air multiplied by the molar flux of acetone over the total molar concentration multiplied by the Maxwell-Stefan diffusivity for acetone and air. And then similarly, the same thing for methanol. Same thing, we're just going to replace like the 1 with 2. So it's going to be Y2 N1 minus Y1 N2 over C Maxwell-Stefan diffusivity of 1 and 2 plus Y2 and 3 minus Y3 and 2 over C D 2, 3. So here is the Stefan Maxwell equation. So at first glance, seems a little difficult. But if we take a look at it, what do we have? We have Stefan Maxwell diffusivities for each pair. Well, that's given to us in the problem already, so that's not a big deal. What about the total molar concentration? Well, assuming ideality in the vapor phase, that's just equal to P over RT. That's the total molar concentration. And we know P and T, R is just a constant. We can calculate the total molar concentration. So everything here in the denominators right here is just, it's just some value that we'll calculate. So it's no problem. Up here though, we have Y1, Y2. We have the mole fractions of each component. So for this differential equation, having the mole fractions of acetone and methanol is no problem because it's a differential equation. We're trying to solve for those anyways. Having those in the differential equation is no problem at all. When we have the mole fraction of air, Y3, that seems like to add a level of complexity to our problem, but since the mole fractions have to add up to 1, that is just dependent on the mole fractions of acetone and methanol. So the mole fraction of air is just 1 minus the mole fraction of acetone minus the mole fraction of methanol. And so really what we have here is a two-dimensional first order linear system of differential equations, except that if we were to try to write it in that form, we actually have these coefficients, the molar fluxes, molar flux of acetone, molar flux of methanol. Those are unknowns. The molar flux of air, as we discussed before, that's just equal to 0, so that will cancel out and that will cancel out. But we still have these unknowns in our differential equation, the molar flux of acetone and the molar flux of methanol. We know that it doesn't vary in position, so if we plug some initial guess into these differential equations, we'd be able to solve it with our initial conditions that the molar flux of, the mole fraction of acetone, the initial one, which is at the liquid vapor interface, is equal to 0.319, so that's for acetone. And the mole fraction of methanol at the liquid vapor interface is equal to 0.528, that's for methanol. If we knew the molar fluxes of each one, which the molar fluxes are just the rate of evaporation, if we knew those, we'd be able to solve this system of differential equations with our initial values. But if we were to just choose some molar flux of acetone and molar flux of methanol, if we were just to choose these arbitrarily, we'd get a solution to our differential equation, but the problem would be that the solution would have the mole fractions of each component being equal to their mole fractions at the liquid vapor interface. That'd be correct, but at the far end of the spectrum, where z equals 0.24 meters, where z equals delta, that would not be equal to 0 unless we chose the correct molar fluxes of acetone and methanol. And so the idea here is that we're going to use the Python programming language to define a function that inside, well, we're going to define a function that takes in the molar fluxes N1 and N2. Since N3 is equal to 0, that will end up canceling out. We're going to define a function that takes in these two molar fluxes, and then nested within that function, we're going to solve this differential equation right here. And then that function is going to return the mole fractions of each component at z equals delta. And at z equals delta, we're supposed to have the mole fractions of acetone and methanol be equal to 0. And so we're going to use a root function to be able to calculate the correct array N1 and N2 that satisfies this differential equation to make the values of the mole fractions of acetone and methanol at the extreme z equals delta be equal to 0. Because this differential equation itself, it's solvable no matter what N1 or N2 you put in. But for this problem, there's only one pair of N1 and N2 that will satisfy the mole fractions being equal to 0 at z equals delta. But in order to use root functions, especially with computers that use numerical analysis, they use iterations, so they use some kind of algorithm to be able to come up with the root of a function. If you want to calculate the root of a function, you have to first have some kind of estimate for what the root of the function is. So say x squared, right? We're trying to find the root of that function. You put that somewhere way out there, not even near what the actual root of the function is, the computer will not be able to converge to the actual solution. So our part, although we're going to be using a computer to actually do all this work for us, we have to put in some work for ourselves. We have to be able to calculate some kind of estimate for the molar fluxes, so that when we do the root function, it will ask for us to put in an initial guess. And our initial guess has to be somewhere within an order of 10 magnitude of the actual answer. So on our part, we can't rely on the computer. We have to put in some work ourselves, and we have to calculate the order of magnitude estimate for both N1 and N2. And so what we're going to do now is that we are going to first scale this differential equation. And so we're going to introduce a variable. We're going to call it, we can call it anything we want, but we're just going to call it eta, because I think eta looks really cool. Look at that. Pretty, huh? Okay. Eta is equal to z, the position, over delta. And what did we do there? Instead of z going from 0 to 0.24, instead we're introducing a new variable which goes from 0 to 1, because we're dividing by the maximum value of z in our differential equation, which is z equals to delta, because at that point it's equal to 0. And so this is what we call scaling. And this is important because it allows us to take things that are, diffusion could occur across a couple nanometers. It could also occur over a couple kilometers. You're able to take those two different things and be able to scale them to where they're both, even though one's going from 1 nanometer to 2 nanometers and one's going from 1 kilometer to 2 kilometers, you're able to take those two problems and they're both scaled to where it's the 0 to 1. And that makes things much simpler and makes everything, you have some reference frame for size of things. This also becomes important when you talk about non-dimensionalization. So this eta here, z has units of meter and delta has units of meter. So if you cancel those out, there's no dimensions. It's a non-dimensional variable. And later on, in some of my later videos, I'll talk about some non-dimensionalization. And when you non-dimensionalize equations, actually what happens, it makes your job a lot more simpler. It actually takes the number of parameters in your problem and is able to convert it down according to a thing called the Buckingham pi theorem, which I'll talk about later in some of my other videos, but it makes our problems much more simpler. So what we're doing here is we're just scaling our z direction so that the mole fractions at any position eta, eta ranges from 0 to 1. And so what's this do for our equation? So if we consider the derivative of one of the mole fractions with respect to z, that's just, if we use the chain rule from first year calculus, that's the derivative of the mole fraction with respect to eta times the derivative of eta with respect to z. Easy stuff, easy peasy. So that right there is just the chain rule. It's still equal to the derivative of the mole fraction with respect to z. But what is the derivative of eta with respect to z? That's just 1 over delta. So dyi, either one of the mole fractions, derivative of one of the mole fractions with respect to z is equal to 1 over delta times dyi. So derivative with respect to not z, because I did scale this, otherwise this would be pointless, with respect to eta. Okay, so let's rewrite these Stefan Maxwell equation. Let's rewrite it. Take into account that, first of all, the molar flux of air, as we discussed before, is equal to 0. The mole fraction of air is linearly dependent upon the mole fractions of acetone and methanol, because it's 1 minus, they all must add up to 1, so this must be 1 minus the mole fractions of the other two components. And then we're going to plug in this relation right here, so that we'll have a scaled differential equation. So if we do that, I'm going to simplify some algebra. So dyi over dz, it's 1 over delta times the derivative of the mole fraction with respect to eta, but I'm going to take delta to the other side, but then I'm going to put it in the denominator. So I'm going to skip some steps because if you're watching this, you're smart enough to be able to do some simple algebra. So let's do this. Okay. So derivative of the mole fraction with respect to z. So we're going to just put derivative of the mole fraction of acetone with respect to eta. That's equal to, so you can kind of follow along. Let's keep it up here. So we're going to have this, but then I'm going to take delta and put it in the denominator. So y1 n2 minus y2 n1 over, keep breaking this, c d12 over delta, right? Because delta, yeah, delta. Minus, because this is equal to 0, and then y3, the mole fraction of air, is just 1 minus the mole fractions of the others. 1 minus y1 minus y2 n1 c3. All right, and then we'll do the same thing with methanol. Don't ever drink methanol, by the way. Even if you like alcohol, don't drink methanol. It's different than ethanol. It'll kill you. Okay. y2 n1 y1 n2. I'm sorry that this portion is boring, but algebra is boring, so I can't make this fun. y3 is 1 minus, yep. So this is our differential equation when it's scaled, which is pretty awesome. Cool. But if we're going to use the root function, we need to be able to have a some kind of initial guess for our molar fluxes if we want it to actually converge, because it's going to use an iteration method, and if we use some arbitrary, just random value that's crazy, not even close to the root, the computer's going to be like, you're an idiot. No, I'm not doing this. It diverges. You're not going to be able to get a solution. So you need to get at least a ballpark estimate of what it actually is. So we consider here on the right side the mole fraction. What is that? That has an order of magnitude estimate of 1, because mole fractions go to 0 to 1. Eta goes from 0 to 1, so you can say that the slope of the mole fraction with respect to eta at any point, we can say that that's about an order of magnitude of 1. So what's that mean? That means that this term here has to have an order of magnitude of 1, and this term here has to have an order of magnitude of 1. This was I kind of wrote this horribly. Okay, N1, that was not an M. I looked at that and I was confused. Okay, so if this over here, this has an order of magnitude of 1, this over here has an order of magnitude of 1, which means that the order of magnitude of this on the top must be the order of magnitude of this on the bottom. If we do a rough estimate, since we're dealing with gases here, well, first of all, let's get rid of this. This right here is delta. That's goes from 0 to 1. That has an order of magnitude of 1. The Stefan-Maxwell diffusivity has a magnitude about 10 to the negative 5 for gases and vapors. So that's 10 to the negative 5. And then the total molar concentration is P over RT. R times T, temperature is 300 Kelvin about, and R is 8, so that's about 2400, so we'll say that's about 10 to the 3. So we have 1 over 10 to the 3 times 10 to the negative 5. But the pressure, we have the pressure, which is up here, which is 100 times 10 to the 3rd, which is 10 to the 2nd times 10 to the 3rd, which is 10 to the 5th. So 10 to the 5th times 10 to the negative 5th is about 1 over what we had for the R times T, which is 10 to the negative 3. So that's 10 to the 3. So it's 1 over 10 to the 3. So that's 10 to the negative 3. So in the denominator here, I don't want to write all this out, so I'm just talking out loud. So the denominator here is 10 to the negative 3, so therefore we know that up here must be 10 to the negative 3 in order to keep the order magnitude of this entire term equal to 1, and because this over here, the order magnitude of this is equal to 1, and since the mole fractions are an order magnitude of 1, then the molar fluxes of acetone, methanol, and acetone must be on the order of 10 to the negative 3. And we'll check this out eventually. Because we're going to solve this. So we're going to say that the order of magnitude of molar flux of acetone approximately equal to the order of magnitude of methanol. It's all approximately equal to 10 to the negative 3. And this is important because this is what we're going to import into our root function to be able to calculate the actual molar fluxes of each. So we're going to do this in Python. And I'll show later that if you plug something in that is outrageous and not even close to this number, the computer isn't going to be able to actually calculate it. It's going to diverge. So this is very, very important. This is going to be our guesses for the molar fluxes of each. And then afterwards, we'll see how close these initial guesses actually were. This is a very, very powerful technique, because without doing anything on your own, not using any program software, not even calculating anything on your on paper, you're just able to like sit there and intuitively know that the order magnitudes of the molar fluxes of acetone and methanol, which is the rate of evaporations, is about 10 to the minus 3. So that's pretty important, and I'll see you in the video where I do the Python coding, and we'll actually solve for the molar fluxes of acetone and methanol, and then we will graph the concentration profiles of each component with respect to eta. All right. So now we're going to talk about programming out what we talked about in the first part, but we're gonna do this in Python. So the first thing, we have to import the necessary functions we need to be able to solve this problem. And so since we're trying to solve a initial value problem, as we discussed the Maxwell-Stefan equations, it's a system of a two-dimensional system of linear first-order differential equations. We need a solve IVP function, and Python has a package called SciPy, which has a module called integrate, and inside integrate there's a function called solve IVP. It's inside the module called integrate because solving differential equations is a form of integration. We don't want the entire module integrate, so we just want that one function because we don't need all the other functions and everything else defined inside that module. So we're just going to import that function from that module. So from scipy.integrate import the solve IVP right there. And as we talked before, we're going to use the computer to do an iterative method to be able to solve the roots, which are our molar fluxes of acetone and methanol. That is, there's a function in the SciPy. There's a module inside SciPy called optimize. There's a function called root that we'll be able to use to be able to implement that into our program. So we just want the root function of it, so we'll just import the root function from that module inside the SciPy package, as we did with the solve IVP. We don't want all the functions inside the modules because we're not using all of them. So from SciPy dot optimize import root. Awesome. So those are the two functions we're going to need to be able to solve our problem. So here, right here, I have all the parameters from the problem. So I have the Stefan diffusivities, which are used in the Stefan-Maxwell equations. We have the Stefan diffusivity for acetone and methanol, and then Stefan-Maxwell diffusivity for acetone and air, and then the Stefan diffusivity for methanol and air. Right there, and the units are there. We have meters squared per second. We also know the pressure and temperature, which remains constant, we assume throughout the entire process. So converting those to Pascal and Kelvin, we have 99.4 times 10 to the 3 pascals and 328.5 Kelvin. And the R, which is just the universal gas constant, that's 8.314, and that is units of joules per mole per Kelvin. From that, assuming ideality of the vapor phase, PV equals nRT, so N over V equals P over RT, which is N over V is equal to the molar concentration, total molar concentration. That's equal to P over RT, so we can calculate the total molar concentration. We also know delta because we're scaling this, and eventually when we do this, we do the programming to solve this, we're going to be using our scaled version of the differential equation. So our delta there is equal to 0.24. And we, when I talked about this in the first part, there were the parameters and the denominators. So each derivative had a pair of 3 terms in the denominator, which is just a number, as we see here. It's equal to total molar concentration times the Stefan-Maxwell diffusivity divided by delta. That will just make our code much more easier when we introduce the terms, because instead of typing out that entire term in the denominator, we can just say F12. So we have all those terms that were in the denominator, and then we have our initial values for our solve IVP function. So with all of that, let's just, first thing first, we're trying to solve an initial value problem, so let's look at that function. So solve IVP. The first thing is we need a function. I'm just going to write that as fun for now, for function, just how it has listed up there. I'll come back to that in a second. And what is T-span? That means if we look down here, T-span, interval of integration, so from T naught to T final, because most problems have to do with time, but this has to do with position, so it's from Z initial to Z final. Since our differential equation has to do with eta, and we scaled it, that's from 0 to 1, so we'll just plug in 0 to 1. All right. Nope. All right. And then what's next? We also have our initial values. So we already know our initial values. Our initial values are at where Z equals 0, which is the liquid-vapor interface. So that's just the vapor pressures of each of the components, acetone and methanol. So we already had those imported up here. So y1i and y2i. And with this function, we can actually choose the method that we want. My professor, and I trust my professor, he likes the method which uses Raudau, something like that. However you pronounce it, that's the method he likes. That's the method I'm going to use, and I trust him because he's way smarter than me. So, method equals Raudau. Raudau. That's how you spell it, right? Raudau. Do. Hold up. Can't remember how it's spelled. I guess I should know because he's whoever Raudau is. He's smart. Raudau. It's an A. So I was right originally. There we go. And then we'll send dense output equal to true. this is just going to be able to allow us to evaluate the solution at any point eta, so anywhere between 0 and 1. That's awesome. So let's go back to the function which I was originally talking about. So this function is something that it's a function that you have to define in this Google Colaboratory environment. Jupyter Notebook, Python, whatever you want to call it. It's just a function. You can call the function whatever you want. You don't have to call it fun for function. I'll call it diffie because it's a differential equation. And the requirements for this function is that the first argument has to be the independent variable, which is eta, right? And then the second argument of the function has to be the dependent variable, which is just y, which is an array, where the first element in the array, index 0, is just the mole fraction of acetone, and the second element in the array is equal to the which has an index of 1, is equal to the mole fraction of methanol. And this function has to be the right-hand side of the differential equation. And since I don't really want to type it out, I already have it saved in here. I'll just copy and paste it. Let's hope it works. Boom, that's the right-hand side of our equation. So we want this to return this, but it doesn't know what y1 or y3 or y2 is, so this y, which is an array, the first term is, the molar fraction of acetone, second term molar fraction of methanol. We'll just say that y1, this is just some trick in Python. You could just say y1 y2 equals y, since y is the length of y is 2. So Python will know what's going on. Lucky for us. So y1 y2 equals y, but what about this? y3 we don't know, but we do. y3 is just equal to 1 minus y1 minus y2, because, well, y3, the mole fraction of air, is not independent of the other mole fractions, because the sum of the mole fractions must be equal to 1. Sorry, air. So that is there. So if we do solve initial value problem, right there, if we say fun, it's not going to know what to solve, because we renamed it to Diffie, because I like the name Diffie because of the Diffie. So we'll say Diffie, and if we run this, surprise, surprise, what do you think is going to happen? I'm going to bet that it cannot solve the differential equation. Although it's a computer, it's much, much smarter than me. It's not going to be able to solve the differential equation. Why is that? Because, well, there's some parameters in there that it doesn't know. Which is the mole fractions of N1 and N. I mean, not the mole fraction, the mole fluxes of acetone and methanol. It's not going to know what that is, so it's going to be like, you didn't provide me enough information, and yep, there it goes. N2 is not defined. If it were to continue after N2, it's going to tell me that N1 is not defined, and it's going to be like, can't solve this because you didn't provide me enough information. I'm a computer, I'm smart, but I'm not that smart. So, unfortunately, until those days where computers can do everything for us, we're going to have to import something. So what if we just say that N1, we're going to import our initial guesses. So if we say N1 and N2, like the molar fluxes of acetone and ethanol, we do our order of magnitude estimate for them, which is just 10 to the negative 3 and 10 to the negative 3, right? Definitely should not be a dot, otherwise Python will yell at me. So, right. Now I'll be able to solve it because it knows what N1 and N2 are. But unfortunately, what I imported will not be correct. So this is kind of like a class with different properties. So I can take this and I set it equal to result. If I take that result and then I want to access the property solution and then evaluate it, let's see. With our initial guesses, let's see how close we were. We know with our initial guesses that if our initial guesses were correct, that the mole fractions at delta, which is at eta equals 1, that should be equal to 0. So we'll just go ahead and see if we were correct, essentially. So solution, so result dot, so solution property, it's kind of like a class. Solution, and we're going to evaluate it at eta equals 1, which is at delta equals 0.24 meters. And let's see how well we did. Oh boy, what did we do? Well, I don't know where that came from up there. I guess I accidentally put a dash. Ah, there we go. So here we go. We get our mole fractions at z equals delta, and that's, well, the mole fraction of acetone is negative. Imagine that. And the mole fraction of methanol is 0.86, so it's 86% methanol. Well, that is just not the correct answer because we know the mole fractions are supposed to be equal to 0. So if we just come up here and we just kind of mess around with it, let's say the molar flux of acetone is 1.5 times 10 to the negative 3, right? I don't know. Let's say the other one, molar flux of methanol is 2 times 10 to the negative 3. I don't know. Let's see what happens. Ooh, we still get negative, and then we get the mole fraction of methanol being equal to 1. So what we could do here theoretically is just come here and change the values of N1 and N2 until we satisfy the boundary condition that at the extremes, that z equals delta, at eta equals 1, that the mole fractions are equal to 0. I mean, we could play around with those. I'd be sitting here for a while. Luckily, we have the root function from the SciPy optimize module. So we want to be able to use the root function. We need a function that we're trying to set equal to 0. And since we want the mole fractions to be equal to 0 at eta equals 1, we're going to define a function that takes in the mole fractions and then returns the mole fractions at eta equals 1, and then we're going to run the root function to be able to calculate the molar fluxes of acetone and methanol, that's N1 and N2, such that the mole fractions of acetone and methanol, Y1 and Y2, are equal to 0. So we're going to define another function here, and I'm just going to call it function because I am lazy. So it's going to take an N, which is an array, which is the first element being the molar flux N1, and the other element being N2, which is the molar flux of methanol, right? Since I want to make all of this local variables, I'll just indent that to make it like that. It's not going to know what N1 or N2 are, but N1 and N2 are just the elements in N, which is a array with 2 elements. So I could say N1 and 2 equal to N. It's just a trick, something, as long as you import, say, the number of arguments if the number of things you say are equal to a list, the length of the list, then it will work out fine. So n1, n2 equals to n. Define function, right? Result equals diffy. That works. Result dot solution 1. So we want to be able to return result 1. And as long as I hit shift enter here, nothing bad happens. There we go. So let's see, function. So let's say our n, our molar fluxes of acetone and methanol are what we initially guessed. So 1, so 10 to the negative 3, 10 to the negative 3. We'll get the same answer. Boom. Doesn't make any sense. So we can sit here and we can play around with that forever. Or we can use the root function, which will find the molar flux of acetone and the molar flux of methanol that satisfy this, so that the mole fractions of acetone and methanol at eta equals 1 or z equals delta is 0. So we're not using the ROR function, we're using the root function. And so the function we want to import is what I called just fun function. And then our initial guesses, and this is where our initial guesses become very important from the first part. So we're going to say 1 e to the negative 3, so 10 to the negative third, and same thing. And what happens? Boom, the solution converged. Now, what if we just choose like a random value for the molar fluxes? Like, let's say each one was equal to 1 mole per meters squared per second. Let's see if the computer could solve it. I'm going to say it did not solve it based off that. I don't know what that is. So let's say 1 e to the, say, negative 6. So 10 to the negative 6. 1 e to the negative 6. Oh my gosh, the solution converged. You say 7. Let's see what happens. Solution converged. I actually did this before, and I think it's around like 10 to the negative 10 where the solution does not converge. Oh, there it is. Boom. So our initial guesses are important. Otherwise, the root function, although it's amazing and it does things that I don't know what it's doing, but it solves it for me, I need to provide it something for it to be able to solve it. So if I just use some random value, it's not going to be able to solve it every time. So there we go. Root, boom. And so we're going to say that we'll set this equal to result. And we'll then be able to access the molar fluxes of acetone and methanol. So N1 and N2 is equal to res dot x. I think that works. If we just molar fluxes. Boom, there we go. So 1.7 times 10 to the negative 3 and 3.1 times 10 to the negative 3. Our initial guesses were correct. So now that we have that, we'll just have we'll define a function which is our actual answer. So answer, which is solution to our initial value problem, it becomes a function of eta. So we'll say a function of eta equal to we'll just import this here, control copy, res dots, solves the initial value problem, right? And we do have N1 and N2 specified now, so it'll solve the initial value problem with the correct molar fluxes of acetone and methanol. And then we're going to return res dot solution at eta, right? And I'm pretty sure when I do this at 0, it's going to be all confused. Nope, it's not confused. It already did it. I think it's because I ran Diffie already in the global scope. But if I would have written this out like this explicitly, Diffie would not be in the global scope. So I'd have to actually define it. And here is a global variable, Diffie, right? To be able to access it. But I already ran it before I actually defined the actual function, so it's already in the global scope, so I don't actually have to go through and define it as a global variable function. So answer, so our solution, what's the mole fractions of acetone and methanol at eta equals 0? Boom, boom, boom. What is that? 0.319.528, which is our initial values. And then our answer at z equals eta, essentially equal to 0. That's awesome. All right. Now we want to be able to, we can grab the mole fractions of acetone and methanol at any point eta with this function, the answer function. We just plug in any value of eta between 0 and 1, and we'll get the mole fractions of acetone and methanol. And from that, we can calculate the mole fraction of air, because the sum of all the mole fractions equals to 1. So we're going to want to plot this, actually. So before we plot, we need to get our independent variables. So what do we want to plot? We want to plot eta from 0 to 1, and we want any number of points that you wish. I like 100, so I'll say that eta equals I for I in range 101, so that's going to give us 100 points, which will be, I want it to go from 0 to 1, so it's going to be I over 100, so that's going to go from 0 over 100 to 100 over 100, which is 0 to 1. You can even just see what eta is, right? Boom, there we go. It's 101 points. And then if we do answer of eta, boom, we get the mole fractions of acetone. There's a list of 51 points, and then a list of 51 points of the mole fractions of methanol. And so we want to plot this. And keep in mind that it's a list of lists, and the first element in the list is a list of the mole fractions of acetone. It gets kind of confusing, but so in order to plot, we're going to use Plotly, because Plotly has some good interactive graphs. So actually, I don't want to import all of Plotly. So from Plotly, graph objects, no, subplots. We want to make a subplot. Subplots as import make subplots. That will give us a function that allows us to make a subplot, which will just be one plot, and then on that subplot we want to be able to add a graph object. And the graph object that we want is a scatter. Boom. Okay, so figure. This will be our graph. We'll just say make subplots. We'll say rows. So it's just be one by one. Let's see what our figure looks like. Boom. Nothing on it. Not that interesting. So we're going to add a trace. It needs a graph object, so we're going to use a scatter plot, and x is equal to eta as we defined above, and then y is equal to just our answer evaluated at eta. But again, that gives us a list of lists, but the first list in the list, which has indexes 0, is our mole fractions of acetone. So this will be 0. That will give us our mole fractions of acetone at every eta, and then we'll just call this, we can give it a name, acetone. That looks good. Let me just make sure. Awesome. So that worked. And now I'm just going to copy this. Ugh. So this one will also, we're going to add a trace. Again, same eta, but instead of it being the first element in the array, it's going to be the second one. Know that Python starts at index of 0, so that's eta 1. That will be not acetone this time, but methanol. Not that it matters, but let's clean it up and make it look nice. And then this third one will be air. And since the mole fraction is just equal up to 1, that's just going to be one minus the mole fractions of each. Boom. And now if we want to make this kind of look cooler, put up here, we could change the default of this, change the colors of it. This is why I love Plotly. You might be able to do this in Excel, but I don't know how. But this is just so beautiful. And here you can drag your cursor right here and just see what the mole fractions of each one are. It's awesome. You can change the color of it. So import plotly.io as pio, right? And then you can choose the different templates. I think you can get a list. There we go, we get our list. So our default templates. So none, that's just what we have. My professor likes Plotly Dark, but let's just choose one at random, and let's just use Seaborn. That would be cool. So pio.templates.default equals Seaborn. I think that will work. Nope. Case sensitive. Just case sensitive. There we go. That's Seaborn. And here we get a graph of the mole fractions of acetone, methanol, and air as a function of eta. So any point here, you just put your cursor over it. So 0.94 here is just eta, and then the second element is the mole fraction of each. And I agree with my professor here, and I think this isn't as pretty as the other default templates, so I'm going to change this to Plotly dark. I think so. Yeah. Boom. Yeah, I think that's much more pretty. Alright, so that's it. Thank you for watching, and I hope you enjoyed. Thank you.